Hi, everyone. I'm Justin Maresco, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on benchmarking ASCE 4117 evaluation methodologies for existing reinforced concrete buildings. The report NIST GCR 2291750, published in 2022 by the National Institute of Standards and Technology, forms the basis of today's webinar. This webinar is made possible with funding from the ATC Endowment Fund. The purpose of the ATC Endowment Fund is to support efforts of critical importance to structural engineering design practice, research, and education. And more information about the ATC Endowment Fund can be found on our website. If you haven't already, you can download the handouts using the link in the Zoom chat. We know that many of you are interested in receiving professional development hours for your participation today. Registrants who would like a PDH certificate must attend the full duration of today's webinar and pay $25, which helps ATC cover some of our costs. A link for purchasing a PDH certificate is in the Zoom chat and will be provided via email following the webinar. PDH certificates will be sent within 4 weeks to all those who attended the full duration of the webinar and who paid the $25 fee. If at any time during the webinar you have questions, please type them in the Q&A window in the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar. Please submit your questions as you have them rather than waiting until the end to submit them. We'll answer as many as we can given our available time. A link to the recording of today's webinar will be posted to the events section of the ATC website in coming weeks. So now let me tell you about your presenter today. Russ Berkowitz is a principal at Farrell Elsesser Structural Engineers in San Francisco, with more than 28 years of experience providing structural engineering services on a variety of new design and retrofit projects. In addition to his firm-related work, Russ is a contributor to many seismic code and standard committees, including ASCE 7, where he serves as the chair for the nonlinear code provisions, ASCE 41, the BSSC NIHRP provisions, and ACI 369. Russ served as the project technical director for the ATC 134 project, which led to the publication of NIST GCR 2291750. I'd now like to turn the webinar over to Russ. Russ, please go ahead.
Thanks, Justin. Again, thank you everyone for being here today. I wanted to thank everyone for attending, and big shout out to both the National Institute of Standards and Technology, NIST, and the Applied Technology Council for all their support on this project and for inviting me to present for you today. This project took place over 2016 to 22. It didn't seem that long when we were doing it. It seemed like we were always rushed, but time flew by, and we wrapped up our work in 2022. It was funded by NIST and managed by the Applied Technology Council. We had a great project team that had our project technical committee, our working group members, project panel, and review panel, and NIST. We had a really good combination of practitioners, so we could have people that really use the document working on it. Lots of academics and professors. A lot of the people that developed some of the information that's in there were involved. And then members from various firms and students were able to help with the analysis. But again, I want to have a big shout out to both NIST and ATC, specifically Aisha for keeping us on track, and Siamak from NIST, who had lots of great input. They were very critical to making sure we got things completed on time and put together a great document. Where does this project fit in the overall ASCE 41 development? The evaluation of existing buildings was fairly first documented with ATC 14 back in the mid-80s. Then that kind of led to the series of documents, FEMA 178, 310, and ASCE 3103, which also covered the evaluation of existing buildings. Then beginning with FEMA 273, then FEMA 356 and ASCE 4106, we had documents developed that talked about seismic retrofit and rehabilitation and evaluation of those buildings in the rehabilitated state. beginning with 4113, the evaluation and retrofit was consolidated into one document. Then kind of that moved into ASCE 4117. And one thing I wanted to highlight there is the ATC 124 project, which led to FEMA P 2006, which gives some great design example and guidance on proper use of ASCE 41 and how you do some of the things. And then that was based on 4113, but took in some of the upcoming things that were to come out in 4117. And then kind of here we are in the top right corner. So both NIST and FEMA have funded many research projects. I highlighted a couple there, ATC 114, which is recommended nonlinear modeling provisions for different types of buildings. Our ATC 134 project there, which is studying the behavior of concrete buildings. And then also ATC 140, which these are paid programs where we do research and development and come up with ideas and information that can be considered for inclusion into subsequent versions of ASCE 41 or other standards. So for instance, this project work developed information that was able to be used by the committees for 4123 and then ultimately for future 4129 consideration. I wanted to say that really NIST or FEMA, they don't tell ASCE 41 that you need to use our research information. They just kind of set the table by doing some paid research and to develop information that can be considered in the standards development. I'm going to be moving as quick as possible to make it in time and leave some things for time for questions, but I did want to highlight that what I'll be describing here has been summarized very well in the August 2023 earthquake spectra, where we had 2 articles, one of which noted there on the left on the nonlinear results was picked for editor's choice in that publication. So if possible, I would like for you to look for those EERI spectra papers, because what I'll be summarizing very quickly today is summarized quite nicely in those 2 documents. Outline of today, we'll talk a little bit about how we picked the buildings we were going to look at and how we were going to analyze them and what our approach was and general observations. Then we'll talk specifically about the nonlinear analysis provisions, then on to linear analysis, and then conclusions and recommendations for future work. We really looked at various assessment procedures, including FEMA P58, FEMA P2018, which is looking at the collapse probability of concrete buildings, Eurocode to some extent, and the New Zealand guidelines. But our main focus was really on ASCE 41. So while we did look at those other documents and methodologies and have information in our document on those studies, we won't be focusing on that today, again, because our main focus was on ASCE 41. All of these documents are performance-based. And so we really want to see how well do they predict overall observed damage in real earthquakes and shake table tests. We wanted to include some shake table tests because those take out a lot of the other uncertainties, soil structure interaction, non-structural, and so forth. So if we can't get those right, there's little hope that you can get an actual building correct. And then we also wanted to make recommendations for future standards updates. The contract had some requirements for what types of buildings we were going to be looking at. We were only looking at reinforced concrete structures. At least 2 of those buildings needed to be from the United States. At least 2 buildings had to be frame buildings, and one of which from the US prior to 1980 to cover non-ductile detailing. At least 2 shear wall buildings, one from the US prior to 1980 as well. Up to 2 shake table tests was allowed, again, for the reasons I stated earlier. Ultimately, we ended up adding one additional building from Mexico City, a Puebla earthquake of 2017, and one additional E-defense shake table test. So we ended up having 3 shake table test studies. So you'd think there'd be lots and lots of these buildings to choose from, but when you started to go through these selection filters, it became a little bit harder to find candidates, and the list becomes a bit reduced. So we wanted buildings to be similar to buildings in the United States and not have really bad quality of workmanship, that sort of thing that may affect the results. We wanted the buildings to really be regular if possible, to take out some of the uncertainties related to irregularities. We needed to have detailed post-event reconnaissance survey data documenting damage. We really wanted to know where the damage was, how bad it was, kind of spaced throughout the building rather than just a few random photos here or there, so that we could tie our evaluation results to what was actually observed. We needed detailed building information, obviously, about drawings, photos, etc. We needed really close recorded ground motion data. So we didn't want to just estimate the ground motion data. We needed to use recordings that were either directly adjacent to the site for instrumented buildings, or as near as possible for real buildings. And then we have the shake table testing information from the shake table tests. And to the extent possible, having some soil information as needed. Kind of a quick summary of the buildings we looked at. The first was a 2D frame tested at the UC Berkeley shake table tests. There's a couple of unique things about this, in that the columns on the left had really ductile detailing with closely spaced ties. Columns on the right were the ties were spaced more far apart, giving you non-ductile behavior. The test results basically had significant damage to the column here at the base, this non-ductile column. And we additionally had some joint damage and a bit of beam damage as this column began to lose axial capacity due to the crushing damage. Loads were distributed out and caused a little damage to the adjacent elements. We did a 4-story concrete building that was tested on the E-defense shake table in 2010. You'll see 2 buildings actually on the slide. One of them had post-tension shear walls, the other one conventional shear walls. We looked at the one only with conventional shear walls. The test table was subjected to the Kobe earthquake ground motion. And the kind of damage seen, you see some photos there, was significant joint damage at the beam column joints, some spalling and crushing of the base of the columns, as you can see in the top photos. And then the wall had some crushing flexural damage that initiated, and then it was followed by sliding. So the wall ended up having a sliding mechanism during the testing. The 6-story Imperial County Services building, constructed in '91, was damaged in the '79 Imperial County earthquake. This building was instrumented with 13 accelerometers spread over the height of the building. Some significant features here were the discontinuous concrete shear walls. You see one in the front face here. And there was also a step back of the gravity system, so that there was some discontinuities there. In the long direction of the building, it was concrete frames, perimeter frames. And then in the short direction, transverse, it had these exterior discontinuous shear walls. And then there are shear walls at the interior of the building in the transverse direction. You can't really make it out in the photo. Another thing here, you'll see, I just wanted to have a detail here. On the bottom right, you can see that while the columns had really nice tie spacing above the pile cap, the concrete slab and everything went up so high that it kind of restricted things, and the failure happened above where the ties were closely spaced. The Van Nuys Holiday Inn is a 7-story building constructed in the 60s. It was designed prior to the 71 or the 71 San Fernando earthquake, so it had non-ductile detailing. Had a little bit of damage in the 71 San Fernando earthquake, very minor though, but suffered significant damage in the 1994 Northridge earthquake to the perimeter moment frames. There was some damage to some slab column frames at the interior. The building did have some masonry infill as well, was instrumented. The damage was really concentrated at the 4th and 5th floors. You can see some column failures there, shear failures of the columns. The Pine Gould building was a 5-story building in New Zealand. Many of you know this building, constructed in the 60s. It had a little bit of damage in the 2010 Darfield earthquake, but ended up collapsing in the 2011 Christchurch earthquake. This building, again, had some vertical discontinuities in the gravity system. As you can see, the columns step back towards the interior at the lowest level. And in the earthquake, that first level was effectively undamaged with all of the collapse mechanism taking place above that level. The core suffered a compression flexural failure in one of the walls, which then led to a rigid body rotation and excessive drifts in the building, which then caused overall collapse. Another building we looked at is the 3-story Nanhua District Office building. It's one of 3 buildings in this area that were damaged in the 2016 Taiwan earthquake. It was designed in the 60s with the exterior concrete moment frame. It had some masonry infill as well, some of which was partial height, some full height, but with some windows and some areas that created some captive column conditions. The damage included shear cracking. You could see a little bit of that in some of the exterior columns and spalling of the concrete columns, and lots of damage to the full height masonry partitions. Another building we looked at towards the end of the project was the Miramontes building. It's a 10-story building from Mexico City, designed in the 70s, effectively equal to about the 71 ASCE code. It was damaged in the 2017 Puebla earthquake. It had shear walls in one direction, concrete shear walls, and then moment frames throughout, lots of CMU infills as well. The damage to this building was significantly to the CMU infill, with very little damage to the actual concrete elements. And then the last building study was a 10-story building tested on the E-Defense shake table in 2015 that had concrete moment frames in one direction, and then in the other direction, concrete shear walls and moment frames combined. Damage was really high concentrations of damage was to the joints, and then some minor spallings of the columns and yielding at the base of the columns and walls. But that damage was pretty modest compared to the joint damage. Now kind of switching gears to talk about our modeling approaches. So really our main theme for this was follow ASCE 41 as much as possible. 41 doesn't give all the guidance you need. Sometimes you need to kind of invent some things or think about things and bring in other standards, but follow it as much as possible and really make it a blind prediction. Don't try and look at the damage and then figure out how you're going to model it to try and emulate that damage. We want to try and see if we could have predicted the damage prior to knowing what it was. Again, the modeling is similar, but not identical for all buildings. We had different teams working on different buildings, just like you would in the real world. So there was some different choices made by the teams on how they would model things that were mostly similar, but not identical. Our nonlinear models used a combination of lump plasticity and fiber elements, and we'll talk about those in a bit. And then the linear models follow the ASCE 41 effective stiffness recommendations, pretty much verbatim without straying from that. So now, how did we compare what we saw in the observed testing or observed earthquake to what our simulations were doing? So for the instrumented buildings, we had lots of great engineering demand parameters and by EDPs. So we knew the force in some elements. We knew how far the drifts went, and we knew what the accelerations were on the floor. So we were able to use those directly. For non-instrumented buildings, we did a couple of different things to try and track that. So on the left, we know FEMA P58 has some photos of elements in various damage states, and then it has associated drift demands at those damage states. So we could, from a damage state, look and say, okay, what would P58 have suggested for a drift? Then we had lots of testing data that we had with reports on testing, with graphs and figures of the damage at different levels of drift and so forth. So we looked for testing that had been done on elements that had very similar detailing and axial loads and so forth. So if we could look at the damage we saw in the field, could we then look at the tested data and then estimate what the drifts might have been for that? When we look at kind of the different acceptance criteria, we used, for buildings that we saw the damage, we said, well, how would we classify this damage? Was it immediate occupancy? Was it life safety, or is it collapse prevention? And so what we did is we turned to the table in the appendix, or excuse me, in the commentary of ASCE 41, which describes qualitatively some damage states. So you see for collapse prevention, it shows what type of cracking and where it might be, what life safety might mean as far as damage. So we looked at the damage, and then we said, which of these categories does that kind of look like it fits into? So then we could assign it collapse prevention, life safety, or immediate occupancy. When we look at the global response metrics that we were looking at, so the first thing we were looking for is, could we identify the critical mechanism? And by that, we mean the location of peak response and the mechanism type. Which floor had the highest acceptance ratios and the peak drift-related damage? We wanted to see how well the overall distribution of damage was predicted. So if we got it right on one floor, were we right on all the floors, and kind of the overall extent and distribution of damage, rather than just looking at one individual element. And then for the instrumented buildings, obviously we wanted to make comparison of the simulated versus recorded engineering demand parameters. So that was kind of globally what we were looking at. On the component side, kind of locally, we're saying, are critical components correctly identified? Again, are the elements with the highest acceptance or DCRs being correctly identified? And then are component response mechanisms correctly identified? Are we predicting flexure when it was shown to be shear, or are we getting shear correctly, or was it an axial failure, that sort of thing? And then overall, did we predict the severity of damage accurately? Okay, so taking a quick step here, we're going to go now summarizing the nonlinear results. And again, I'm going to just present some things here kind of quickly that shows, what our overall findings were. But I will refer you to the actual document to download and the EER articles for some more detailed explanations of this, because given the time, that this is going to go by kind of quick, so I do apologize. Our key questions for nonlinear is, how well do the nonlinear models represent structural response, the location and severity of the damage, the need for retrofit, where do the ASCE 41 nonlinear procedures succeed or need work? So those are kind of the key questions, again, summarizing what we've talked about before. As far as nonlinear modeling approaches, we left it up to the individual teams to decide how they were going to be doing things and how they would model things, because ASCE 41 provides latitude in that respect. So we also, just to point out, we use two different modeling software. Sometimes it was done with OpenSeas, and sometimes it was done with Perform 3D. And in some cases, we did both. We have a Perform 3D and an OpenSeas model. You'll hear me talk about lumped plasticity. So those are kind of in the top left, the concentrated plasticity models. Some teams chose to use fiber sections for columns and beams, kind of a distributed plasticity, as you can see in the kind of top middle. For joints, we did a number of different things. Sometimes nonlinear joints were used. Sometimes linear joints were used, and then we looked at kind of what is currently in ASCE 41 and some other types of joint models that are out there for looking at kind of backbone behavior. For masonry infills, the newer versions, ASCE 4117, doesn't really provide great guidance on kind of how you do masonry infill or how you might consider struts. So we kind of went back a little bit to FEMA 356 to get some guidance on that. So staying faithful to 4117, but using a little bit was in FEMA 356. For wall elements, kind of OpenSeas, there was a couple things. One thing you'll see is that's the MVELM, the multiple vertical element line model. That's got nonlinearity from the vertical elements and then a nonlinear shear spring. And then from Perform 3D, we use the layered shell element, which many of you may be familiar with. All the structures were modeled as 3D with bidirectional ground motions for the nonlinear response history. We used the ground motions that were closest by, like I said. We used 3% damping as is specified in ASCE 41 that generally consisted of a combination of Rayleigh damping and modal damping. And again, we really didn't want to try and guess at how we should model things based on the damage. We really wanted it to be a blind test. So you can see here, there was a number of different decisions made and taken with nonlinear modeling of elements. I won't spend time on each one, but just wanted to show the wide variation that was chosen by the teams to do the work. And then other things we considered is, some different variations of linear elements versus nonlinear elements. So for instance, joints, we looked at it linearly and nonlinearly and so forth. Looking at the acceptance criteria, so a curve you're all well aware of. So when we were looking at the components, we were looking at the acceptance criteria here, as you can see. When we look at kind of component damage, we follow the ASCE 41 backbone, and the parameter little a you see there represents the point of lateral strength loss. Parameter B is kind of the end of the test, or when you might expect to lose all vertical load carrying capacity and lateral capacity of an element. And kind of to support these comparisons of kind of where we were on these curves, as I mentioned, we looked back to some tests that have been done, looked at the component damage and so forth, so that we could try and look at where we would be acceptance criteria for life safety, immediate occupancy, and so forth. And then on the global side, again, this is a replay of that previous table. So when we're trying to say globally, what does this building look like to us? We relied on these ASCE 41 commentary descriptions of the various loading or damage states to try and say globally, where does this building fit? Looking at the results now from our nonlinear analysis, looking first at story mechanism comparisons. So this is looking at the level of the building that had the highest level of damage or response. And did we capture that level of the building in the general location? Well, a green with an M is a match, and a red with an NM is a non-match. So wanted to kind of point out a couple of things here. For the E-defense test, which was the concrete shear wall building, the wall sliding was not captured in our model. ASCE 4117 really doesn't have any guidance on sliding, and it was not considered as a failure mechanism. So that one was missed. So the model actually captured the fact that we had a flexural wall problem, which looks to have instigated the sliding, but we didn't capture the sliding itself. The Pine Gould building, the model had nonlinear shear and flexure in the shear walls. And what we found, and when we modeled the building and simulated it, is that the second story shear wall showed a shear failure, which essentially created a soft story condition. And that was not observed in the real behavior. As I mentioned, it was a flexural compression failure of the shear walls. Once we tried to use an elastic shear material, which you would not have chosen to do. Really, when you're just opening up 41, you would have thought this wall should be behaving nonlinear and shear. But once we replaced that with an elastic shear material, we were able to emulate the collapse pretty exactly. For the Van Nuys Hotel, this building, we were a little bit off on the story that had the most amount of damage. And another thing is that the damage was really to the columns, when the model simulation and hand calculations would have told you the damage should have been concentrated in the beams. And we'll talk about that more here soon. So now focusing on how well did the nonlinear methods predict the peak story drifts. Now, there's lots of dots in here, and this, just to know, this is only showing results at the critical story. So the story having the highest level of damage. You'll also see dotted lines with plus and minus 20%. That's kind of what we considered a good match. This plot only shows the instrumented buildings. So generally, we did a pretty good job in that plus and minus 20%. A couple of them were outside of that. One in particular is the Open Seas model for e-defense, because Open Seas at the time didn't have a great PM lump plasticity model. We were under predicting bi-directional and axial interaction demands on those columns. So we under predicted the drifts compared to reality. But generally at the story levels with the greatest amount of damage, we were pretty close with our nonlinear drift simulations. Kind of away from that area, away from the area of most damage, the results were, mixed. There wasn't any great trend. So what happened at the stories that weren't the critical ones? So the two on the left showed that our simulations under predicted the damage, or the drifts at those levels away from the highest concentration of damage. Versus the one on the right shows that the 4-story e-defense test, our model was predicting much higher drifts up in the building than we compared to the actual recorded motions. That one may be attributed to the fact that we didn't capture the sliding, which may have changed the accelerations and forces up the height of the building, but that's just one theory on that. So kind of away from it, there wasn't any really great trends. And if you can see that shown here in this plot, this is for the measured buildings, the ones where you had shake table tests or were instrumented. This shows the peak story drifts at all the stories, so not just the critical stories. And you can see there's no real great trend either. It's not biased towards being conservative or unconservative with our evaluation simulations, but there's just a lot of scatter. And so just take that into consideration. And just know that, many times these models are used for use in risk or damage or loss estimation. So say if you're doing a P58 assessment where you really want to know the drifts at all the stories, we were seeing that you could be off, more than 20% in most cases, and even higher, 40–60% at lots of other cases. Residual drifts, we said let's look at it, but they're really, really hard to analyze for and get correctly. It really depends on how you're modeling the hysteresis pinch shaped and how well your software can capture that. But kind of in general, you see here, our simulated residual drifts were almost always much higher than what was seen or observed. So if you're using these kind of things for a loss estimation, just know if your residual drifts probably aren't right, and we couldn't ever have a really good chance of predicting those correctly. Now, kind of moving on to peak floor accelerations, we'll talk about the roof and throughout the buildings. So the roof accelerations are indicated with a square box. Frame directions got the blue dots, and the wall directions got the black triangles. You can see that there's pretty significant scatter in the peak floor accelerations between simulated and measured. At the roof, we did a pretty good job. I would say those results were closer, but in general, there's a lot of scatter. You can see this goes to plus or minus 60%. So again, this speaks to if you're using a 41 type of model to try and predict accelerations, just something to think about. You may be pretty far off in considering your uncertainties for those loss estimations. In the frame direction, we generally, the accelerations were generally over predicted, and in the wall direction, we under predicted in some cases. And so lots of reasons this could happen, but we have some theories for each of the different buildings, but no real clear trend other than a little bit of over prediction perhaps. Moving on now to kind of component failure mechanisms. So what we're looking at here is, are we matching a failure mechanism? So if you see a green M, that indicates the components had a shared failure mode with the observed damage. So we got flexure or shear correct. So we did a pretty good job here, as you can see. There's a few non-matches we'll talk about here. So again, the OpenSeas test and the Perform 3D for the E-Defense one, we weren't able to predict that sliding failure of the wall in our model. Pine Gould, we've talked about that we were not able to predict the wall failure correctly. So we ended up having a building that collapsed, but when we looked at some of the actual beam joints and so forth, we had a non-match for that reason, because the way our story mechanism formed versus in reality with that consideration of shear. For the Van Nuys Hotel, our models showed that the damage should have been concentrated in the beams. And so we over predicted that versus the reality where the columns actually showed the damage. We'll maybe talk a little bit about why that might be later, but that was one where we really missed it. So if you do a hand calc, you would show you have strong column, weak beam. When you run an analysis, it tells you that. But then when you look at the reality, the failures were all in the column. So we did miss that one. Talking now about the component damage at the critical location. So looking specifically at the component level, we were kind of interpreting that based on the backbone curves again. So where you would pass the little a point would be where you begin to lose strength. And then the B point being where you lose all strength. The highest variation in damage comparison, as you can see from the table, was really with columns, with about half the models over predicting column damage and about half under predicting column damage. I mean, we got the mean right, but we were kind of up and down with the columns. Beams tended to be over predict damage, so we're on the conservative sides. But this shows we had pretty good agreement for the most part on the damage. A specific example kind of shown here. We have the observed damage on the left. So kind of yellow dots would be minor damage, with red being more significant damage. The frame and the wall kind of shown on the left and the right there, versus the simulated damage. So we had under prediction of the column damage in the frame direction. You can see on the left there was more cracking and spalling versus the one on the right where all the dots are white. Simulated didn't show so much damage. As I mentioned, we were able to predict a failure of the wall, but we missed the mechanism type. The simulated was a flexural issue versus the sliding failure that was seen in reality. Component damage, another example, just to kind of show you some things here. We had the observed damage showed the diagonal cracking or flexural cracking. You can see on the left where diagonal cracking is shown by the red squares and flexural cracking predicted by the orange squares, versus our simulated, where we had a lot. You can see where we were a little bit less than the A point in some cases, so not showing strength loss. So lots of similar locations, but maybe the damage was a little bit different. Speaking about component acceptance criteria now. So if we're looking element by element at immediate occupancy, life safety, and collapse preventions, all of these buildings really had a lot of damage with the, well, a fair amount of damage. So when we talk about, whether we matched the immediate occupancy or life safety or collapse prevention, we were really focused on collapse prevention, given that these were high damage buildings. And so it's hard to say how far above or conservative our collapse prevention simulations were above what it is in reality, because kind of once you're above collapse prevention, it's hard to say how far above it you are. But in general, we matched that. So we were getting components correct for the most part. We did, again, have some under predictions in a couple of cases, as I mentioned, to the columns and to the joints at the Pine Gould, and then over prediction of some beam damage as well. Now focusing on kind of the global acceptance. Again, most of these buildings were classified as collapse prevention or near collapse prevention. So we were generally getting that performance level correct. However, since most of these buildings were somewhat poor performers, this finding indicates 41 is good at finding those poor performers, but we really didn't focus at all on immediate occupancy or life safety, or that was a lot less of our consideration. We were really trying to see how well it predicted near collapse or collapse performance. Excuse me. Again, the Pine Gould building, you see that we had a not match for global, and that's again because our models predicted a shear failure of the wall, whereas that was really a flexural failure. So instead of a kind of soft story shear mechanism, it had the crushing failure of the wall, which led to a rotation and more of a failure, pushed the failures all throughout the height of the building. And for the Van Nuys Hotel, you'll see again, that was one where we had predicted damage to be in the beams from our models, but it was overall in the columns. So we called that, kind of a not match because it was really the wrong locations and the wrong elements that were predicted for failure. So kind of some general conclusions from our nonlinear models. Our predictive performance generally matched the observations. We were able to find poor performers, but these were all pretty poor performers. The results generally tracked the critical components and the location of critical damage and the drift at that area. So where we're really trying to find where is the most vulnerable portion of this building, which elements or what type of damage, we generally did pretty well with that, but we missed it on some other cases. Things that nonlinear analysis had difficulty in replicating was the drift and damage at other locations. So away from the main story that had the highest concentration of damage, our drifts were kind of somewhat okay at predicting that, but we were off to an extent that we would have not liked to have been. A little bit higher scatter at those locations away from that highest level of damage. Peak floor accelerations, again, were kind of all over the place. We were sometimes good, sometimes bad, but that is really difficult to replicate. And those 2 points kind of, again, are important when you're looking at using this ASCE 41 modeling and acceptance to create nonlinear models for use in loss estimations and risk assessments. And to try and, if you're trying to use those engineering demand parameters from the nonlinear analysis, you maybe have some considerable uncertainty at some levels, and you need to consider that with the uncertainties in those loss estimations. And then also complex failure modes. How do you look at, joints that are bidirectional, beam column joints? That's a hard one to get right. Wall sliding. There's now some guidance in ACI 369 and ASCE 4123 that talk about wall sliding, but that's a tough one to get right. Is it the flexure that leads to wall sliding? That's one that's still a hard thing to actually evaluate in a nonlinear model. Other things is, again, the shear strength of wall cores. I'll put that as something as a complex. Like, you have these return walls that could offer some shear resistance when you're looking at in plane, versus out of plane shear. So do the out of plane core walls kind of protect against shear sliding a bit? That's a hard one to predict, or actually to model. And so how can you do that? Another thing that's difficult and that we ran into difficulties with is when you have adjacent elements that have really similar capacities, and we'll touch a little bit about this later as well, so when you have joints whose shear capacity is really close to what the beams or columns can deliver, or when you have beams and columns that are really closely matched in their capacities, the nonlinear model really will concentrate damage in the element that you selected to have that lowest capacity. And you may miss some damage that due to uncertainty in material strengths and so forth. So the nonlinear did have difficulty kind of looking into those complex failure modes. So, areas for improvement, some overly conservative beam backbone properties, that has been taken care of for the most part in ACI 369. Some other things is a guidance on axial moment integration and PMM biaxial considerations. You have to select a axial load to use to create your backbones in many cases and your acceptance criteria. And that's dependent on an axial load that you don't really know. Do you use the axial load as the maximum from the analysis, or is it based on a pushover? Some better guidance on that would be helpful for PMM interaction. Again, improve shear wall modeling behavior. That is being handled in the 369 process, ACI 369. Improve guidance on calibration of fiber models. So you have a fiber model, say for a wall or a column or a beam, and it's really pretty easy to get the backbone to match your fiber model when you're doing a monotonic push. But when you have cyclic behavior of the fiber models, sometimes you see some funkier results as your individual fibers kind of yield or crush, go through their motion. Does the overall cross-sectional behavior still match the backbone? Because all of the backbones, again, are based on overall cross-section behavior, not individual fibers. So giving some improved guidance on how you might calibrate fiber models so that the overall section matches. And then for the masonry buildings, it's just really tough to model that masonry infill we found. So any improved guidance on that would be helpful moving forward with the nonlinear methods. Jumping now over into the linear procedures. So linear procedures are used probably most of the time. They're less sophisticated, but they're more accessible. There's the assumption that they're expected to be more conservative, but maybe not always. One thing, that is obviously apparent to engineers that do this and to all of you is the linear models have no ability to redistribute demand. And so finding out what that means globally in a building can be tough, and we'll talk about that. But even when you do a nonlinear analysis, a linear model is generally the first step in doing a tier 3 kind of nonlinear evaluation. I did also want to point to a little bit of previous work that had been done. A couple of papers that you may find interesting. This one here, the main author was Siam Akhtatar, and he was looking at studying ASCE 7 buildings. So if you design a building that's with ASCE 7, and then you go ahead and evaluate it using ASCE 41, how well did that building perform? And I can tell you for the linear procedures, this paper found kind of similar to us that it's maybe overly conservative. Nonlinear dynamic did a pretty good job, but linear might have been a little bit conservative. Similarly, the NIST document by Harris and Spiker, this was also, again, looking at ASCE 7 designed buildings and how they performed if you evaluate them with ASCE 41, found similar trends. So I just wanted to make you know of these papers because these also have some great information that you might find useful. So for the linear, again, key questions. Are they really conservative? Is 41 really conservative compared to other methods? And so, does the real damage match the observed damage? And how does the linear procedures compare to nonlinear procedures? And then we wanted to look at, where the linear procedures obviously succeed and need work. These buildings, we didn't look at all of them using linear analysis. We only looked at these here that you see on the screen, 6 of the buildings. Software was generally either ETAB, SAP, or OpenSeas. We looked at different linear methods. Only one of the buildings did we do the equivalent pseudo-static method. Others, we used response spectrum analysis on them, as you see. And then for all of them, we used response history analysis as well. So doing a linear time history on those buildings. To evaluate the component demand to capacity ratios or acceptance ratios, as they're better defined now in ASCE 41, we have the demands due to earthquake and gravity loads. We have our component modification factor M. We assumed our knowledge factor was 1 for this study. So whenever there's a kappa K, we always assumed 1, and we use the expected material strengths. For the force-controlled actions, similarly, we assumed a kappa of 1 and based it on nominal or lower bound strength. So we generally had the drawings, and that's what we used for our nominal strengths. We did look at, the M factors as well. So their M factors are tied to the same performance states as nonlinear acceptance, but are generally more conservative. Since we're not simulating strength degradation with a linear model, the M factors are really calibrated such that you don't get beyond the point at which strength loss occurs. So your collapse prevention M factor is about here. In general, they're maybe 25% more conservative than the nonlinear acceptance criteria. One thing I will say is we did look at, well, what if we just increase the linear M factors by 25% to kind of better calibrate them to nonlinear? And we found that actually gave unconservative results. So it's not as easy as saying is that the M factors might be a little bit more conservative. There's more to it than that when using the linear methods. We looked at the quantitative comparison between linear and nonlinear. So the classifications of immediate occupancy, life safety, or collapse prevention, or beyond collapse prevention. And then qualitatively as well. So again, as I mentioned, we looked at that damage and then tried to tie it back to this table that you have in the ASCE 41 commentary. So look at how big the cracks are and how would we quantitate that based into the collapse prevention, life safety, or immediate occupancy. Again, just like nonlinear, we looked at global and local response. So looking at the global response is, looking at the overall acceptance ratio throughout the structure. How well were we able to predict IO, LS, or CP when we mapped it in that way? And noting that ASCE 41 is really an all or nothing with the linear procedures, right? If you have elements that fail collapse prevention or your selected criteria, that means failure. So we took that into note when we were looking at our global response. For the structures that were instrumented, we compared story drifts and rift accelerations. Now, that's not really directly part of ASCE 4117, but we just wanted to see if by looking at that, we could find any other trends that may be useful for us to look at. Modeling approaches, we used the effective stiffness values from chapter 10 of ASCE 41, as you can see there. Beam column joints, again, we modeled as shown in there from ASCE 41. Generally kind of models that looked about like that in ETABS or SAP or OpenSeas. Just a quick summary of the different types of elements. Again, linear, it was a little bit more straightforward. There's not as many selections you have. But some things that are different is sometimes the joints we had a true joint flexibility considered. Sometimes we use that rigid offset model. So those were looked at a little bit differently in linear, but that didn't have much of an effect on things. Damping was 5% modal or rally damping, just like we have in 4117. We used accidental torsion amplification just to see what that would do as appropriate. For the linear models, we had fixed column and wall bases, essentially with no soil structure interaction. One hard part, I will say, if you're trying to do a pseudostatic or even a response spectrum for this study, is we have kind of not a design spectrum, which is nice and smooth. We have the actual recorded spectrum, which kind of jumps all over the place. So if you're doing a linear model and you have such jumpiness and your period is off by some amount, you could be really off in the demand. So we attempted to try and smooth the spectra. And what we did is kind of a multi-step process. Is we first took the ground motions and we ran them under different damping assumptions from 2% up to 20% and got spectra for that. We then modified those spectrum to shift them to what they would be in an equivalent 5% by modifying each of those spectra by the B1 parameter you see there. That's in ASCE 41, chapter 2. Then after we brought them all up to the 5% equivalent, we took the average of all of them and kind of smoothed it out. And that's what you see on the right. So we did a little bit of manipulation to try and be able to have a bit smoother of a spectra to work with when we did the response spectrum analysis and the static analysis. Looking kind of at our results, we really had, this is just for buildings that had measured period information. And again, know that these simulated periods use those effective stiffness values, and that our predictions of periods was significantly higher than the periods of the buildings. Now you're seeing here the periods of the buildings based on ambient noise. So these were the periods of the tested or in place structures that were instrumented before the earthquake came along and damaged it. Then if you kind of look at this plot here, This shows the shift in periods. It's lots of things to see here, but what it's showing here by these blue arrows is we were able to look at what our non-linear models predicted as the periods after the shaking, and then looked at what the measured results after the shaking would be. So you can see that kind of shift. And generally, again, we tended to be higher than our simulations produced higher periods than the measured periods, with a couple of exceptions that are described in the document. Looking now towards story drifts. And again, this is the drift at the critical location. So the story that had the most amount of damage. The linear simulations tended to under-predict the drift at the location with the most significant damage. Across the board, you can see most of those dots are down below the line. For the Van Nuys building, we had to do a little bit of estimation. So even though it was instrumented, it wasn't instrumented right near the location with the most damage. So we had to estimate the drifts, and that's why you see a bar, those represented by bars. This shows the critical story. At the non-critical story, we were sometimes over, sometimes under predicting drifts with linear. There was no really good trend with that. And I will show one thing here, kind of for the UC Berkeley, again, when we're looking at the damage, you see the damage here shown on this figure. With green dots, this is what was actually observed in the field with kind of no damage, and orange dots with some moderate levels of damage, and red dots showing severe damage. You know, that red dots is there at the critical story. So again, looking at the drifts, we got the drifts pretty close. You see the three green lines are the different linear methods we chose to use compared to the heavy black line. So our drift was a little bit lower than the measured drift at that critical story, but then we had big levels of over prediction of drift away from the level that had the critical behavior. Sometimes up to 90% over prediction of drifts from the linear methods away from the level of critical behavior. Looking at linear versus nonlinear, it shows kind of similar trends. Again, with the linear drifts on the vertical axis, nonlinear drifts on the horizontal axis. So at the critical story, you can see the trend in that it was a little bit lower drifts predicted by linear versus the nonlinear. Accelerations are pretty much useless from the linear models unless the building remains totally linear. You know, we're not, you know, sending any new, giving you any new information here, but just we did measure them, and we significantly overestimate the accelerations in the building with a linear model. We just don't have a way to capture that the mechanism formation and how that might lower the demands. The other thing is, you know, our stiffnesses are kind of chosen on that effective stiffness value that could vary up the height of the building in reality, but you kind of pick one for everything. So we were really off with the roof accelerations with constant over prediction. Excuse me, one moment, I want to take a sip of water. When we compare linear to nonlinear, we see that same constant over prediction for in accelerations, as I mentioned. Now moving on to component behavior. So looking at each of the elements, IO, LS, and CP. This is for linear versus observed. And this kind of matches what most people's assumption is that you either match or you over predict. So linear methods were either matching what we saw in the observed for the most part, or over predicting it in many other locations. Kind of globally, what does that mean? Well, not a lot to be told here, again, because if we're constantly matching or over predicting, as you can see with the predictions in the far right column of the overall building. We call this building class prevention versus just component. We were, pretty much matching or over predicting in all cases. Again, I wanted to mention this over prediction of damage globally. This shows one of the test frames. Again, we've seen this image before, but up in the upper stories, very little damage. You see lots of green dots. But then when you look at nonlinear dynamic analysis versus linear response spectrum analysis on the left and right, respectively, the linear showed lots of damage all throughout the building. As you can see, those upper floors show lots of elements beyond collapse prevention that are just not observed. And again, that's because there's no way to capture that mechanism formation and how that redistributes and kind of creates a fuse and makes the loads above be a little bit less. So in general, it was really hard to get a global prediction with the linear on the overall level of damage throughout the entire building. So we did look at 6 buildings with the different modeling approaches and the different linear methods. Again, these were all heavily damaged or collapsed buildings, so it's hard to really say for sure what would happen at other levels of damage or at immediate occupancy or life safety. Kind of our main conclusions is that the predicted performance generally matches the observation. So the components, that are greater than CP performance tracks with the heavily damaged elements in the building. We're generally finding those critical stories and failure modes with the linear methods, but overall we over predict the severity damage. More components being damaged than were observed. The distribution is also more widespread with those linear. That could be due to, different crack stiffnesses and obviously the non-consideration of a formation of a mechanism. There's no significant difference in the outcomes between the linear procedure types. So static response spectrum and linear response history were all pretty similar to one another. And then overall, both nonlinear and linear were able to reliably identify the main vulnerabilities, the most critical. Nonlinear, again, provides a better understanding of the damage distribution and the global mechanism. Linear procedures could really be enhanced with some consideration of a mechanism analysis, and that's something we're considering for future work on how you might do that. Similar to what's done in FEMA P 2018. Some kind of general observations and key takeaways is, like I am summarizing and kind of saying things again here, but linear and nonlinear were able to predict the correct mechanism location. We got the right story for the most part. Linear generally overestimates the overall damage distribution. Again, I don't think that's a surprise to anybody, but the extent was confirmed in everything we did. Nonlinear provides better drift distributions over the height of the building. So that could be important when you're trying to identify specific vulnerable components which are in need of retrofit design. So that's going to get a much better picture from the nonlinear analysis methods. Again, saying linear methods really need to have some way of considering a mechanism formation to be able to limit forces elsewhere in the building. Kind of the key positives is the critical, the location of critical damage, again, is located. The drift at that critical location is pretty well predicted by both methods. And the overall performance of the building is pretty good. It could be better. We did have trouble with some mechanism predictions, as I mentioned, beams versus columns versus was it the joint or wall sliding. So we generally had the right location and concentrations of damage, but the actual mechanism prediction could be better. The drifts away from critical locations could be improved. And that global level of damage with the linear methods leaves something to be desired. And the distribution of kind of other drifts throughout the building could be improved. Looking at kind of recommendations for future work, as I've mentioned, beam modeling has been improved with ACI 36922. Wall sliding is now included in ASCE 4123 and ACI 369. The joint modeling is still is a tough one. You know, when you look at the strengths, you have a gamma factor for how many squared F prime C you are with the joint. You know, it's one number. You pick 20 or 15 or 10 or 8. And if you're off and you have a hinge for that, and that becomes your mechanism, you could be protecting elements that may not really be protected. So joints could probably use some improvement. As I mentioned, we want some improved guidance on modeling with fiber hinges so that those can be calibrated a little bit better to the overall member behavior. We want to have some consideration of material strength variations potentially and bounding and axial loads, and I'll talk about that in a second. And then 41 is really kind of an all or nothing global acceptance criteria, or excuse me, component acceptance criteria. So if an element fails by the letter of the code, you really fail that. But is that true for the building in total? So that's kind of global versus a component is a recommendation for future consideration. Some things, a couple of quick slides here to talk to a couple of those points is, for instance, on the Van Nuys building, when we were predicting beam damage versus column damage, if you look at that, you know, so the real damage was in column shear cracking and some joint cracking, whereas the model was predicting lots of beam damage and almost no damage to the columns. So is that a material issue, or could there be something else? One theory we're looking into moving forward is maybe as these beams have some yielding in flexure, they elongate. And as a beam kind of elongates due to nonlinear behavior, the entire frame would want to get longer. So for buildings where you have a slab that's restraining that movement, that could produce some axial loads in the beams, which kind of, you see a PM interaction diagram here on the right. So if your hinge is really set to be calibrated to what the moment strength with no axial load, versus if you consider what the increase in strength might be due to some axial loads that are generated when the beam tries to grow in length, you can be off by a certain percent, 15, 20%. And that could shift your mechanism if you used a hinge defined with that increased strength away from the beam and into the column. So that's one thing being considered for future modeling considerations in 41. Flexural and axial interaction with linear methods gets really tough. So for example, in this frame, you see down there at the column at the bottom right and the bottom left had that 700, and those numbers in red over 700 for flexure are due to tension. So how do you treat elements that go into tension with linear methods? It's really kind of hard because of the shape of the PM interaction diagram, versus if you see how the nonlinear model treats it. Those elements were shown to have very little damage, not kind of a DCR of near infinity. And you know, you start with an axial flexure interaction diagram, and what forces do you use for that? So if you kind of start with the results right out of the analysis, you could be really far out of the PM interaction diagram, especially on the tension side. And what does that really mean to linear methods? And further, you have to know what axial load you have in the element so that you can enter the table to pick an M factor. What axial load do you use for that? Is it the tension load? Is it the compression load? Some increased guidance on that is important. Also, you need to know what the shear capacity is versus the shear demand, and what axial load do you use for the column when you're looking at what the shear demand might be. What is its flexural strength? You need to know that axial load to pick that shear. So that's another area that we think is in need of improved guidance for the linear methods. These interaction things are really hard when you're using fictitiously high forces. Thinking about component versus global acceptance, Just a quick diagram here. This shows some fragilities we ran for a bunch of motions on the building. And this shows kind of a fragility for when does the first element pass immediate occupancy, shown in green? When does the first element pass life safety? When does the first element pass collapse prevention? Versus kind of more global things of when might an element lose total strength or drift. And so there's a big spread in kind of what the overall global stability of the building is versus when an individual element goes. It's really hard to figure out how to quantify that, but that's something that we're looking at. Sometimes you have a really robust building where, such as the Imperial County, the fragilities would show sometimes you get low levels of columns going, and then you have a lot of significant reserve capacity before all the columns go, versus a Nonlinear type of building where kind of everything goes at once. So maybe then looking at one element does work, versus Imperial County, you may get a false, overly conservative impression of what's going on. Other things we're trying to work on is getting improved drift profiles for linear methods. So one method under consideration, you can see the measured drift in black, the current linear provisions, as we said, kind of over predicting drifts at the stories away from the critical location. And then one method of an improved linear procedure we're looking at right now is shown in blue, where you get a much better match between the linear drift profiles and the nonlinear drift profile. And then just, there's continued improvements with the acceptance criteria. Just an example you can see here for the beams for ASCE 4117 versus 23. And here's the backbone. So things used to be very conservative with the blue, and now they're heading towards the black. And those are being kind of improved for all elements through various things. So I probably went a little long. I went through things really fast, but I wanted to leave the remaining time for questions. And maybe Justin, if you can let me know what I messed up, if somebody can tell me that, or give me any questions, and I'll try and do my best to answer it. And again, I apologize for the speed at which I'm going through this, but we had a short time and I wanted to cover a lot of ground.
Great job, Russ. Nothing about you messing up. We have a lot of really good questions. We probably won't be able to get through all of them, just given the number, but let's give it a shot. Okay, first one, the overall takeaway from the comparisons using nonlinear models seems to be that the predictions generally matched and we're not biased towards over or under prediction. This seems counter to a commonly held belief by practicing engineers that our models over predict damage. What are your thoughts on this?
So I think for the examples we looked at, what I stated was true. I will re-emphasize the fact that we didn't look at buildings that didn't have a lot of damage, right? So imagine you get a 6.0 earthquake that's kind of near your building that had a little bit of damage in reality, but your nonlinear model would show lots of damage. We didn't look at those specific types of examples, so I don't think that I can speak and say conclusively, that holds true for those other performance levels. Some of the ATC projects that are ongoing now is looking a bit more at that. But for this project, I can't say that that is generally true or not. Because again, we were limited to the buildings with a lot of damage already. So they showed collapse prevention and so did our model. So I don't know that I can speak to that.
Mm-hmm. This study suggests that only collapse performance is well captured. Considering this, how trustworthy do you view current performance-based design practice for new mid and high rises, particularly when other performance levels besides collapse performance are targeted?
I'll kind of refer back to my previous statement on that, but again, I'll just kind of say that ASCE 41, if you read section 7.6, it tells you how you generate from test data, how you generate, allowable deformations for collapse prevention, life safety, immediate occupancy. and for what those, how you come up with M factors based on that same data. And really, it's collapse prevention that really defines that. So you kind of start with collapse prevention. Then the other acceptance criteria are not exactly, but are percentages of that. So life safety is a percentage of collapse prevention, and immediate occupancy is a percentage of collapse prevention, or a percentage of life safety. So collapse prevention is defined pretty rigorously in that way in section 7.6, but life safety and immediate occupancy are a little bit more nebulous in the way they're defined. So we didn't look at that in this project, but I have the same wonder about that. So if you're looking at a hospital building where they're saying you need IO and LS at the BSE 1N and 2N, whatever, that sort of thing, we didn't look at how well that predicted that, you know, those levels were predicted. But again, there's that cautionary thing of those acceptance criteria are a little bit more nebulous compared to collapse prevention.
Maybe ideas for future studies.
Yes.
Did you have any records of damage to gravity frame elements that were considered? Did you gather any insights about how well ASCE 41 predicts damage to gravity frame elements under earthquake loading?
Well, for these concrete buildings, we modeled kind of everything. So we didn't consider gravity versus non-gravity. If we thought it contributed to the lateral capacity, it was treated as a primary component and captured. And so I don't, for what we looked at, I can't really separate those two behaviors. But know that, you know, in a concrete building, you do tend to model kind of everything more, versus a steel building with a brace frame or moment frames. You may only have things modeled at the brace frame or the steel moment frame, but that's different than what we had. So we modeled kind of everything, even slabs, you know, and so forth. So I can't say that we had a lot of information on gravity versus non-gravity.
Can you share any insights about the suitability and/or accuracy of different structural analysis software packages? Specifically, what did you learn about Perform 3D versus OpenSeas?
That I can share on this call or in a bar over a drink. I would say it. There wasn't a great trend. I'll tell you some things that became a bit of an issue for the team is that when you use OpenSeas, again, at the time, and I'm not an OpenSeas expert by any stretch, so forgive me if I misspeak a little bit here, but the columns didn't have a great lump plasticity PM element, PM interacting element. So Perform, which does have a lump plasticity PM interacting element, did a lot better job at predicting the behavior of those elements. And so I would say that was one thing that became an issue, that showed some slight kind of bias one way or the other. I think outside of that, sometimes Perform did a better job, sometimes OpenSeas did a better job. But knowing that most practitioners would probably lean towards Perform or some other commercially available software, not OpenSeas, we didn't see any reason to be leery of the use of Perform. It seemed to do a really good job.
How different was the behavior of infill frame buildings and bare frame buildings? Did infill frames behave better? And might this shed any light on the appropriateness of the different treatments between infill and bare frame non-ductile concrete buildings in the Los Angeles non-ductile concrete retrofit ordinance?
The infill kind of helped in many cases, I will say, where it was full height, right? Because it's so stiff compared to the frame, it sucked up a lot of the damage. And it didn't, when it was full height, it didn't lead to damage of the surrounding frame. Where it was kind of partial height and creating captive column condition, it did damage the frame a bit. And in the building in Mexico City that we looked at, the Miramontes building, the concrete basically had no damage, but the masonry was pretty wiped out. There was, cracks greater than 4 inches. So as far as behavior, it seemed like for the most part, the masonry helped because it kind of dissipated the energy that would otherwise have been going to the frames. And they didn't seem to push the frame into a lot higher damage level than if the masonry were not there. So that may not be the case for even larger earthquakes, but I would assume for more moderate earthquakes or an earthquake that's more likely to hit your building, the infill is pretty much going to help unless it creates a severe irregularity, because it just sucks up a lot of the force with, or energy, I should say, without damaging other elements.
Did the simulations consider the aging of the structural system, such as the presence of cracks? If so, could you talk about how you did this? If not, might that help explain some of the mismatch that you found?
We did not consider that. No, we didn't do aging effects on the building. So that was not done in any way, nor is there guidance in 41, obviously, on that, other than is it cracked or is it not? I will say that for the Van Nuys building and the, which other building? The Van Nuys building, and for Pine Gould, which went through 2 earthquakes, we ran the smaller earthquake through the building first, allowed that motion to die down, and then ran the larger events afterwards. So any damage that kind of gets set in from the previous earthquake was at least attempted to be captured prior to running the larger of the earthquakes. So we did run those in series and kind of start with a slightly softer building.
So the knowledge factor equal to 1 is an exception. In almost all real cases, this is likely to be less than 1. Don't you think that this will cause a greater number of mismatches, leading to a great deal of loss of confidence in the practical application of the methods, both linear and nonlinear?
Well, kappa is always a pretty blunt instrument, the knowledge factor. For us, we took it as 1 because we had material testing, right? We kind of had enough information about the buildings that we could justify the use of that kappa. We did not look at, well, what if we really didn't know anything? We were taking a guess and this was 0.75 or something. Obviously, that would have led to much more conservative results. But we kind of knew enough about the building. I will kind of say that in my experience, kappa is one of those things that, especially on peer reviews, you kind of either accept or don't accept, right? It's like, well, we're just going to use kappa of 1. So it doesn't follow 41 directly, but in practice, I would say that kappa is probably one of the least used factors in the evaluations that I see.
I'm not sure if this was even in your scope, but I'll ask it if the study shed any light on other standards like the New Zealand guidelines besides ASCE 41.
I'll say that we looked at those standards. So the New Zealand guidelines, you're really trying to predict how well your building behaves in a pushover type scenario versus a new building standard. So it's not kind of a great, hey, how does this match collapse prevention or life safety? Because you're kind of looking for one specific thing in the New Zealand standard that we looked at. And their models basically say, for modeling, please refer to ASCE 41 or other things. So they kind of tell you to use a model that you probably would have used, we would have used already. So not a lot of differences there. I would say the one thing we did look at a bit, and you'll see lots of discussion on this in our document, is FEMA P 2018, forgive me if I get that number wrong, but ATC 74, which is the collapse prediction of non-ductile concrete buildings. We did look at a series of buildings under that scenario too, and that document tended to predict collapse maybe a little bit ahead of where our nonlinear models would have predicted to collapse. So it could be slightly more conservative for that one. But Eurocode, again, there's not a lot of there wasn't a great deal of ways we could compare things directly. So I can't really say if it's more conservative or not. We did a little bit of look into that, and you can find that in the document. But kind of for today, I don't think there's any big trends that I can tell you because they're so different in what they're actually trying to evaluate.
Great. Thank you, Russ. I think that's all the time we have because we're just about at time. So on behalf of the Applied Technology Council, I want to thank Russ for his presentation, for sharing his experience, knowledge, and insights during the Q&A session. And thank you to everyone for joining us today. Expect to receive a follow-up email with a link to the participant feedback survey, and we really ask that you do complete this because we use that to help inform future webinar topics. If you haven't purchased a PDH certificate and you would like to do so, an email with a link to purchase a PDH certificate will be provided in a follow-up email from ATC. The deadline to purchase certificates is this Friday, February 28th. PDH certificates will be distributed in 4 weeks for all those who attended the full webinar and who paid the $25 fee. I'd like to briefly mention that ATC provides trainings for organizations on a variety of technical topics, such as building safety evaluations after earthquakes, windstorms, and floods, as documented in ATC 20 and ATC 45. For more information, please visit the ATC website. Lastly, our next free webinar is scheduled for April 17th on the topic of seismic performance-based design. Look out for an email announcement in coming weeks. Visit the ATC website for updates on other events and training opportunities. This concludes the webinar on benchmarking ASCE 41 evaluation methodologies for existing reinforced concrete buildings. Have a great day, everyone.